A dull, impure rock lies exposed in the dirt. It is rough, slightly heavier than usual, but entirely unremarkable. You almost certainly wouldn't notice it, and neither did your ancestors. Prehistoric hunters stepped on it every day. Children picked it up only to throw it away. No one gave it a second glance because, to their eyes, it looked exactly like an ordinary stone. Yet buried within that rock is the foundational material that will construct the entire modern world. It is the substance that forms the global electrical grid, makes up the billions of transistors in the phone in your pocket, and provides the skeletal framework for the skyscrapers you walk past every day. Every technological achievement we possess begins with metal. But for the vast majority of human history, those rocks just sat there. The question is not simply how we eventually found metal. The deeper question, the one that will completely change how you look at the technological devices surrounding you, is this. How did an ancient human with no knowledge of chemistry, no industrial furnaces, and no precedent to follow, look at a pile of lifeless dirt and somehow extract a metal that Stone Age technology was fundamentally incapable of producing? The absurdity of this process lies in a basic law of physics. A standard open-air wood fire reaches a maximum temperature of roughly 600 degC. Pure copper, meanwhile, requires 1085 degC to liquefy. Iron demands a staggering 1038 degC. That gap of several hundred degrees is not a minor engineering challenge. For hunter-gatherers, it was an impassable physical abyss. Every logical inference from the natural world at that time dictated one absolute rule: fire cannot melt stone. To understand the sheer madness of this technological leap, you have to understand the world before it. If fire was fundamentally incapable of liquefying ore, by what mechanism did our ancestors manage to wring a shining metal out of the mud? For nearly 2 million years, human technology was defined entirely by subtraction. You take a piece of flint, obsidian, or quartzite, and you strike it to remove material. These stones can be chipped into razor-sharp edges, but they harbor a fatal flaw: brittleness. A stone hand axe can split wood, but a single forceful strike against a hard surface at the wrong angle, and it shatters. Once the atomic lattice of a stone tool is broken, it cannot be healed. But the Earth, in its vast geological complexity, always harbors exceptions. Unlike iron, which has a ravenous chemical attraction to oxygen and rapidly converts to rust, copper is relatively noble. It can exist in isolation. Millions of years ago, under the crushing pressure of subterranean hydrothermal vents, pure copper atoms were squeezed into the fissures of bedrock. Over millennia, erosion from wind and water exposed these mineral deposits in dry riverbeds. In a different context, walking across desolate plains, our ancestors occasionally stumbled upon heavy, dark masses resting unnaturally on the soil, the surviving fragments of nickel-iron meteorites that had violently pierced the atmosphere. Around 8,700 years before the Common Era, in the rugged terrains of the Zagros Mountains and northern Mesopotamia, foragers searching for flint noticed these peculiar heavy rocks. Put yourself in the shoes of an ancient hominid. Following instincts honed over millions of years, you place this strange rock on an anvil stone, raise a hammer stone, and strike it, fully expecting it to fracture into sharp flakes. Instead of shattering, the rock deforms. It flattens. It absorbs the kinetic energy of the blow and yields. At a microscopic level, a phenomenon of quantum mechanics is taking place. In a standard rock, a heavy impact severs the rigid chemical bonds, but in the crystalline lattice of native copper or meteoric iron, the atoms are arranged in a way that allows layers to slide past one another without breaking their bonds. It is ductile. It refuses to be destroyed. The first metallurgical phase of human history involved no fire and no kilns. By patiently cold hammering these native metals, ancient humans shaped them into fishhooks, awls, and small pendants. This completely changes how you must think about the discovery of metal. Our ancestors did not invent smelting to discover metal. They touched it, shaped it, and revered its ability to survive an impact long before they figured out how to pull it from the ground. And that became the driving force of history. Native copper and meteoric iron are incredibly rare. Within a few generations, the streambeds were picked clean. The free gifts of geology were gone. But the memory of a stone that never breaks remained deeply embedded in their consciousness. They looked at the dull, oxidized ores on the cliff faces. They knew the miraculous material was trapped inside. The only problem was that their fires were too weak to release it. The breakthrough that shattered the thermodynamic barrier did not emerge from the hands of hunters. It came from a seemingly unrelated craft: pottery. As agriculture demanded better storage, humans began constructing clay kilns. An open fire dissipates heat rapidly, but a kiln, a semi-enclosed structure with a vent at the top, changes the physics of combustion entirely. Inside a kiln, a column of hot gas rises. As it escapes, it creates a vacuum at the base, aggressively pulling in fresh oxygen-rich air from the bottom to feed the charcoal. Through this simple architectural innovation, ancient potters inadvertently pushed their firing temperatures past 1000 GC. They were finally brushing against the melting point of copper, but heat alone cannot pull metal from ore. If you superheat copper oxide in an oxygen-rich environment, it simply remains copper oxide. To release the metal, you have to alter the atomic structure of the rock. You need chemistry, and chemistry requires darkness. Consider the Vinca culture, flourishing in the Balkans around 5000 BCE. Potters here ground malachite, a rich, vibrant green copper ore, into a fine powder, mixing it with water to paint geometric patterns on clay vessels before firing. When these vessels were loaded into the kiln, and the structure was sealed with mud to retain heat, the environment inside transformed. What should truly astound you when studying ancient metallurgy are the invisible reactions taking place inside the flames. Inside the sealed kiln, the charcoal burns fiercely, devouring the limited oxygen. As oxygen levels plummet, combustion becomes incomplete. Instead of producing carbon dioxide, the starving fire generates a toxic, invisible gas, carbon monoxide, CO. Carbon monoxide is a highly aggressive reducing agent. It is structurally unstable and violently seeks out oxygen atoms to complete its molecular bond. As the carbon monoxide gas swirls upward through the stifling heat, it encounters the malachite powder painted on the pottery. The gas attacks the ore, using chemical force to tear the oxygen atoms away from the copper molecules. The rock does not merely melt, it is chemically dismantled in the solid state. The oxygen is stripped away and exhausted through the roof. What is left behind on the surface of the pottery are pure copper atoms. Under the intense heat, they coalesce into tiny, brilliant liquid beads, glowing a fierce orange, sweating out from the pores of the clay. When the kilns cooled, the potters did not find their expected green glaze. Instead, they found droplets of solidified sunlight. This was the birth of smelting. Ancient artisans did not understand the kinetics of chemical reduction, but they realized that if you placed the green rock in a sealed, oxygen-starved furnace and feed it charcoal, the rock bleeds metal. They had unintentionally engineered an artificial, reducing atmosphere right on the surface of the earth. Extracting pure copper was a monumental triumph. But in practice, it introduced a profound disappointment. Pure copper is exceedingly soft, it is ductile and easily worked but lacks structural integrity. You could expend a massive amount of labor to cast a beautiful copper axe and grind it razor sharp. But the moment you swing that expensive axe into an oak tree, the blade blunts, folds, and deforms. A cheap flint axe would hold its edge far longer. Why then would any ancient society continue to invest colossal resources into a functionally inferior material for heavy labor? The answer lies in human psychology and the divine. In a prehistoric landscape dominated by the muted browns of earth and grays of stone, metal was a visual shock. It caught the sunlight. But copper was not the only metal they found. They also discovered gold and silver. Gold never tarnishes. It does not rust. To the ancient mind, gold was not just a metal. It was a piece of the sun itself, immortal and incorruptible. In many early belief systems, gold was considered the flesh of the gods, and silver was their bones. Using a copper dagger or wearing a gold pendant was about holding attention. It didn't matter if that dagger bent in combat. What mattered was the blinding flash it produced. Metal was born as a luxury commodity, a mechanism for the elite to project divine authority and enforce social stratification. Human vanity, religious awe, and the desire for status financed the greatest technological research project in antiquity. However, as populations swelled and as warfare grew more lethal, aesthetics were no longer enough. The elite needed weapons that wouldn't bend against a wooden shield. Copper had reached its physical limit, but before humanity found the perfect solution, we walked through a very dark, toxic chapter of experimentation. When we talk about the Bronze Age, we usually think of a clean mixture of copper and tin. But history is rarely that neat. Before the discovery of tin, our ancestors created a deadly predecessor, arsenical bronze. Ancient smelters noticed that when they threw certain types of copper ores, ones laced with arsenic impurities, into the furnace, the resulting metal behaved differently. Arsenic acts as a deoxidizer. It removes gas bubbles from the molten copper, making it much easier to cast. More importantly, when cold hammered, arsenical copper becomes significantly harder than pure copper. They had found their superior weapon. But this technological leap demanded a horrifying price. Arsenic is highly toxic. When arsenical copper is smelted, the arsenic vaporizes at relatively low temperatures, releasing a lethal, sweet-smelling white smoke into the air. The ancient smiths, standing over their poorly ventilated kilns, breathing in the fumes day after day, were slowly poisoning themselves. Chronic arsenic poisoning attacks the nervous system. One of the primary symptoms is peripheral neuropathy, a progressive nerve damage that leads to weakness in the legs, muscular atrophy, and eventually, a crippling limp. This dark reality left an indelible mark on human culture, one that you can still find hidden in our mythology. Have you ever wondered why Hephaestus, the Greek god of metallurgy and fire, is depicted as crippled and walking with a limp? Or why Wayland the Smith in Germanic mythology is also lame? These myths are not coincidences. They are the collective cultural memory of humanity. They are a haunting tribute to the generations of ancient, anonymous blacksmiths who sacrificed their bodies, breathing in toxic smoke so that their societies could wield harder swords and sharper plows. The crippled smith is the embodiment of the heavy toll early science took on human life. Arsenical bronze was effective, but it was a dead end. The toxicity was unsustainable. To progress, humanity had to find a safer way to harden copper, leading them to a radical leap in abstract thinking, the alchemy of true combination. Through generations of trial and error, ancient metallurgists began mixing different colored ores into their crucibles. Eventually, someone decided to co-smelt copper ore with a dark, relatively rare mineral, cassiterite, the primary ore of tin. On a mechanical level, tin is an incredibly weak metal. You can bend a bar of pure tin with your bare hands. Basic logic would suggest that melting two soft materials together would yield a similarly useless, pliable mixture. But the rules of the quantum world defy basic arithmetic. When copper and tin are liquefied, their atoms mix. Copper atoms arrange themselves in a neat, uniform crystalline lattice. Tin atoms, however, are significantly larger. As the mixture cools and solidifies, the bulky tin atoms force their way into the copper matrix. They distort the neat rows. They act as microscopic roadblocks, pinning the copper atoms in place and preventing the layers from sliding past one another under kinetic stress. By blending 90% copper with 10% tin, we get bronze. Bronze was a monster of a material. It was vastly harder than pure copper, safe to forge, durable, and held a lethal edge. A bronze sword could shatter a flint spearhead. The marriage of two weak elements had engineered a material strong enough to permanently execute the Stone Age. We often view the mastery of bronze as humanity's triumph over nature. But when you zoom out to the macro-historical scale, a colder reality emerges. We did not simply master metal. Metal dictated the trajectory of our species. The Bronze Age arrived with a devastating geographic curse. Copper is relatively abundant. Tin, however, is a geological anomaly. In the cradles of early civilization, Egypt and Mesopotamia, there were almost no viable tin deposits. The closest abundant sources were located in the hostile, mountainous terrains of ancient Afghanistan, or thousands of miles away on the misty shores of Cornwall and Britain. Before bronze, a tribe could survive in absolute isolation. But once a civilization became dependent on bronze, isolation meant death. If your city-state lacked bronze weapons, the neighboring empire would simply march over your walls and erase you from history. To survive, you had to acquire tin at all costs. This relentless thirst for a rare mineral forced humanity to birth the first global supply chains. Consider the Uluburun shipwreck, discovered off the coast of modern-day Turkey dating back to 1300 BCE. Its cargo hold carried 10 tons of copper ingots from Cyprus, matched precisely with 1 ton of tin ingots sourced from as far away as Central Asia. To transport such staggering wealth across the Mediterranean Sea or through deadly deserts, humans were forced to invent advanced maritime engineering and establish intricate caravan routes stretching thousands of miles. The scarcity of a single element forced isolated humans to connect, trade, and build networks that spanned continents. When you are transporting tons of precious metal across empires, human memory is no longer sufficient. You need an immutable system to record debt, inventory, and taxes. To manage the logistics of metal, humans invented accounting. To make that accounting permanent, the Sumerians pressed a reed stylus into wet clay, creating cuneiform, one of the earliest forms of writing. As wealth concentrated in the form of bronze armories, these trading hubs became targets. To protect their accumulated metal, societies were forced to build massive, fortified walls and transition to standing, professional armies. The management of these armies, the taxation of trade routes, and the administration of written laws gave rise to the first complex states and empires. The uneven distribution of ore on the Earth's crust was the ultimate catalyst. It forced humanity to abandon the egalitarian existence of hunter-gatherers, pushing us into building interconnected civilizations or slaughtering each other to control the resources of the dirt. When looking back at ancient achievements, the modern mind often carries a bias, dismissing the discoveries of the past as mere luck. But history is not built on luck. Our ancestors decoded the physical world without laboratories. They understood thermodynamics through the color of a flame, chemistry through the viscosity of liquid slag, and physics through the recoil of a hammer. Every steel girder and silicon chip today is the direct descendant of an anonymous potter who noticed a droplet of liquid light bleeding from fired clay. The Bronze Age empires believed their shining, interconnected world would last forever. But around 1200 BCE, a catastrophic global systems collapse permanently severed the trade routes. The tin stopped flowing. The bronze dried up. Backed into a corner, humanity was forced to awaken a far more terrifying monster from deep within the earth. The Iron Age. How they tamed iron is a story for next time. If you enjoyed this journey, hit the like button and subscribe to Who We Were to continue uncovering the origins of humanity.